Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 51. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with major significance for monitoring ungrounded system. The ground detection requirement provides the ability to monitor ungrounded system to detect first phase to ground fault on the system. The first phase to ground fault will not cause overcurrent device to operate, so continued service would have been achieved. While annunciation as initiated in the control panel, the operating personnel must have to investigate the actual cause of first phase to ground fault, and that must be eradicated at the earliest possible time. If the first phase to ground fault condition is not to be cleared and a second phase to ground fault would have been developed on a different phase, then there is a simultaneous phase-to-phase short circuit and phase to ground fault event, which may lead to have significant destruction and downtime of the associated equipment. With the perception of higher capacitance in a high voltage, long line, ungrounded transmission system, there may have considerable share of fault current due to transient grounds, that is of momentary grounds and certain instance of lightning. At normal sequence with no first phase to ground fault, then the neutral of ungrounded system remains close to ground potential, and the fault current as due to transient grounds would have been blocked by the balanced capacitance of the three phases. But any occurrence of first phase to ground fault, the neutral that has to shift in potential, and thereby a line to line voltage may have to appear throughout the system between the ground and the two remaining unaffected phases. Figure 165b at part 50. If the fault would be allowed to persist for a long time, then there may have the possibility to fail the expected level of insulation coordination of the connected transformers, rotating equipments, cables, etc. There may have other issues such as the internal overvoltage of a power system, which refers to the increase of voltage due to electromagnetic energy conversion, or may have a transfer of electromagnetic energy inside the system caused by the change in system parameters. These transient overvoltages would therefore be the resultant effect from arcing ground faults as generated through switching of circuit breakers, fault, or other reasons. Transient overvoltages may be classified as the temporary phase of overvoltages, switching overvoltages, or slow front overvoltage, or very fast front overvoltages. The temporary overvoltage that usually has low amplitude, but its tenure would have been for a long time period, if its frequency that would have been equal or close to the power frequency. Sudden increase of voltage on the healthy phase due to resultant effect from an asymmetrical grounding fault may have an abrupt changes in load characteristics as well as to instigate resonance and ferro-resonance effect. Arcing ground is the surge, that is a form of sequential diminishing and restacking, and that is to be produced while the neutral would not be connected to the ground potential. At restacking zone, that can create severe over voltages, and the fault current through it is small but be sufficient to support this arc. Such phenomenon would have to occur in ungrounded three-phase system because of the flow of capacitance current between the conductors when the voltage is applied to it. However, voltage across the capacitances does thus to refer the phase voltage of the corresponding system. During the fault, the voltage across the capacitance reduces to zero in the faulted phase, while in the other phases, the voltage is escalated by the factor of √3 times. An arcing ground fault is therefore a single line to ground fault which has the phenomenon to extinguish and reignite successively. The phenomenon of intermittent arc, which may have to occur in the line to ground fault of a three-phase system with having the consequent production of transients, is thus to be denoted as arc ground. Again, I repeat, the phenomenon of intermittent arc which may have to occur in the line to ground fault of a three-phase system with having the consequent production of transients is thus to be denoted as arc ground. This sort of happenings is mainly due to the presence of a sporadic arc in line to ground fault of a three-phase system. Under some very specific circumstances, these reigniting consequences can cause a voltage escalation. Most important. Salient points in regards to gradual trend of shifting from ungrounded system to solidly grounded or impedance grounded system. At initial stage, most of the systems were ungrounded as it was the natural trend to accomplish that the ground connection was not necessary for the actual transfer of power. But over time, it has been exhibited that the system had some inherent instability due to certain interference of line to ground voltage transients. These transients may have to disrupt sensitive electronic devices and create significant amount of stress on the insulation of the associated electrical machinery. As of the study, These transients are also responsible for imposing a certain possibility of initiating partial, that is, arcing ground faults and ferro-resonance. Sudden increase of voltage on the healthy phase due to resultant effect from an asymmetrical grounding fault may have an abrupt changes in load characteristics as well as to instigate resonance and ferroresonance effect. Transformer core, while that would have to operate very adjacent to its saturation level, then the corresponding B-H curve would also become highly non-linear. See the B-H curve. When a ferromagnetic material is taken through a process of magnetization, then there is a phenomenal relationship between the magnetizing force H and magnetic flux density B of the material. Number two, that is to be represented by the B-H curve. Permeability of the magnetic materials mu equals to magnetic flux density divided by magnetic field strength equals to B by H. The magnetic flux density B that has to represent the actual magnetic field within a material and is considered as a concentration of magnetic field lines or magnetic flux per unit cross-sectional area. And the magnetic field strength H that has to represent to measure of the magnetizing field produced by electric current flow. Hence, the effective permeability of the core material can take on a range of values that vary with the change in magnetic flux density as well as magnetic field strength. However, the hysteresis loss of the magnetic material must have to depend on the shape of the corresponding hysteresis loop, which is also governed by a variety of factors that influence the material's magnetic characteristics. The larger be the area of the hysteresis loop, greater will be the hysteresis loss. Again, I repeat, the larger be the area of the hysteresis loop, greater will be the hysteresis loss. B, greater be the volume of the ferromagnetic material, larger will be the hysteresis loss. C, a magnetic material having a narrow hysteresis loop generally has higher permeability. A magnetic material having a narrow hysteresis loop generally has higher permeability. Whereas a magnetic material having a wider hysteresis loop will have lower permeability. Therefore, the magnetic material has the nonlinear properties such as magnetic saturation, hysteresis loop, eddy current, etc. And due to all these phenomena, the equipment based on magnetic material has occasionally exhibited certain complex responses that cannot be anticipated easily. Ferro-resonant condition is one of the most complex response that can cause as due to presence of the nonlinear transformers magnetizing impedance and systems capacitance in the network. Now I have to discuss with the topic ferro-resonance. What is ferro-resonance? Ferro-resonance is a nonlinear phenomenon and is caused at a specific situation while the nonlinear magnetizing impedance of transformer iron core interacts with the capacitance as exists in the electrical network. Actually, these two components would have to produce a nonlinear tuned circuit with an unexpected resonant frequency, and that has to impose a very high amplitude having with distorted voltage over waveforms. Ferroresonance condition may have to arise when the capacitance of electrical network starts to resonate with the magnetizing reactance of transformer ferromagnetic core, while it goes in and out of magnetic saturation criteria. Ferroresonance phenomenon, which creates very high amplitude and distorted overvoltage waveforms, would have been an obvious factor that against the practice of operating power systems ungrounded. So, in an ungrounded system, the operating characteristics should have been closely monitored and the corresponding sensors must be located as close to the supply source as possible. However, it has been exhibited that potential transformers are the most worst affected equipment. So far, the occurrence of ferroresonance phenomenon is concerned. Ferroresonance condition that is to be often taken place while the electromagnetic voltage transformer interacts with the distributed phase to ground capacitances in neutral ungrounded distribution networks, power systems, disturbances happen. Again, I repeat, ferroresonance condition that is to be often taken place while the electromagnetic voltage transformer interacts with the distributed phase to ground capacitances in neutral ungrounded distribution network as power system disturbances happen. This composite circuit that would have to excite as there must have a significant rise of voltage at the saturation region of the corresponding voltage transformers magnetizing curve, that is B-H curve. There are various reasons that could excite ferroresonance, such as three-phase breakers asynchronously switch on, removal of the single line to ground fault, or abrupt variation of load. As of the subsequent effect, the zero sequence voltage would have to increase, and that may compel to push forward the voltage transformer excitation inductance at its saturation region. This newly formed saturated inductance is obviously of lower parameter than the value of inductance at the normal, that is unsaturated state. At typical frequency, if that core inductance parameter would somehow match the phase to ground capacitances, then ferroresonance may have to occur. As of the subsequent effect of single line to ground fault, the corresponding voltages of that unaffected phases would have to increase by root 3 times, and for which considerably large amount of energy is thereby stored in the phase to ground storage elements, that is distributed natural capacitances between phases to ground. However, during the process of cancelling out single line to ground fault, that stored energy can only be released through the zero sequence circuit path. The stored energy, if it is significantly high, then the flow of current through the voltage transformer excitation inductance would have been larger than the linear current threshold limit, resulting in saturation of its core material and consequently causing to instigate ferroresonance phenomenon. The behavior and pattern of ferroresonance is closely related to the distributed natural capacitances between phases to ground. The frequency of ferroresonance that would have to decrease with the increase of the phase to ground capacitance. Again, I repeat, the frequency of ferroresonance that would have to decrease with the increase of the phase to ground capacitance. As of the fact that the ferroresonance phenomenon is meticulously dependent on the system stored energy represented by the initial values of transformer core inductance current and line to ground capacitance voltage at the time of removal of the single line to ground fault. However, it has also been exhibited that the system stored energy that would have to be minimum while the zero sequence voltage is zero. As a while, under certain circumstances, the ferroresonance phenomenon can occur with power transformers also. Ferroresonance can have to instigate excessive heating of the transformer due to increased peak currents and high core fluxes. It is also to be noted that during the occurrence of ferroresonance, there will be a high level of odd harmonics that are being created as because the transformer ferromagnetic core goes in and out of the saturation. With a nonlinear change of core inductance at the transitions between the saturated and a not saturated core has created a hysteric behavior of the core, which causing to erupt certain voltage transients. Again, I repeat, with a nonlinear change of core inductance at the transitions between a saturated and a net and a not saturated core has created a hysteric behavior of the core which causing to erupt certain voltage transients. Ferro-resonance may thus to instigate excess heating of the transformer due to increased peak currents and high core fluxes. This has made to cause an abrupt failure of insulation as because of the increased electrical stresses. This has made to cause an abrupt failure of insulation as because of the increased electrical stresses. Such overvoltage incidents caused by the ferroresonance that not only endangers the insulation coordination framework of the power supply equipment, but also generates continuous overcurrent which burns out the power supply apparatus, resulting in serious power failure. Now, possible occurrence of ferroresonance, which is an unpredictable chaotic features in power system causing a nonlinear and hysteric behavior of the transformer core. One, lightly loaded transformers that operate in presence of capacitance. Number two, internal capacitive coupling in transformers. Number three, transformer with an open phase of both short and long duration. Number four, three-phase breaker asynchronously switched on. Number five, use of voltage distribution capacitances in high voltage breakers, that is grading capacitors. Number six, use of voltage transformers, that is PT, without any damping measures. Number seven, loss of system grounding, weak grounding, or grounding through stray capacitances. Number eight, use of capacitors in shunt and series compensation. Number nine, use of shunt reactors with saturable ferromagnetic cores. In case of extra high voltage and ultra high voltage system network, the ferroresonance once developed, then its corresponding first cycles of voltage waveform would have become really much more detrimental because the involved frequencies that might have been higher than that of the operating frequency of the system, causing extensive electrical stresses may lead to weaken the insulation coordination system of the network equipment. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.